The Fundamental Theorem of Calculus, FTC Part II. Consider a function, capital or big F of x, and let that be an antiderivative of another function, little f of x. That is, big F prime of x equals little f of x. Now let us find the derivative with respect to x of the integral from some number a to x of f of t dt. My claim is that this equals f of x. Or, what if we did the derivative with respect to x of the integral from some number a to a function g of x of f of t dt? Then this equals f of g of x times g prime of x. I'm going to show the proof for both of these, and then we're going to see how to use this when we actually do problems. This is called the Fundamental Theorem of Calculus. I call it Part 2 because I personally teach it second. So the proof for the first part. Let's do the derivative with respect to x of the integral from some number a to x of f of t dt. We're really doing the derivative of this entire thing with respect to x. So we have implied parentheses there, and in mathematics, we do the thing inside parentheses first. So we're going to do the derivative with respect to x of the integral of little f, which above we called big F, and it's at t, from a to x. By the Fundamental Theorem of Calculus Part 1, the part that I teach first, this says, take our antiderivative, big F, plug in the top limit, x, minus, plug in the lower limit, giving us big F of x minus big F of a. And now we can take the derivative. So the derivative of big F of x is little f of x, as stated above, minus the derivative of a function at a number. Well, a function at a number is itself also a number, meaning its derivative is 0. What if we have a slightly more complicated problem, where we take the derivative with respect to x, and I'll put my implied parentheses here, but they will be explicit in this case, from some number a to a function g of x of little f of t dt. Once again, we will do the Fundamental Theorem Part 1, taking the antiderivative of little f, giving us big F, from a to g of x. And now we can take the derivative of each piece. Where we're going to take the derivative of big F of g of x minus the derivative of big F of a. What is the derivative of this first piece? Well, the chain rule says it's the derivative of the outer piece, so little f, leaving our inside part alone, times the derivative of the inside part minus the derivative of a number, which is 0. So I've shown you the proof for the fundamental theorem of calculus. But how do we use it in practice? Let's take a look at a couple examples at least, maybe 3. Let's find the derivative with respect to x of the integral from -2 to x of sine of t plus t dt. Now, even though I showed how to take the derivative of the integral, we should notice something here. And down here as well. So when I teach this, after I show why it works and how it works, I say don't do the long process anymore. Notice that there are 3 things that happen when we take the derivative of an integral. First thing, the derivative and integral cancel. Second thing, we can plug in the upper limit for the t in f of t, or down here, we plugged in the upper limit, in this case g of x, for every t in f of t. So plug in the upper limit. And then the third thing that happens is that we chain out the upper limit. Why did we not do it here? Well, the chain out, that is the derivative of the inside part, is 1, so we didn't need it. But we certainly needed it down here. So when you recognize what's going on, just follow this 3-step process. The derivative and integral cancel, plug in the upper limit, chain out the upper limit. So how does it work here? Derivative and integral cancel. I'm left with the integrand, but for every t, I replace it with x. And I don't worry about that dt. Notice that dt did not show up here, did not show up here either. It's just there for our theory, essentially. And that's the answer. So what if we had the integral from 1 to x squared of e to the negative t over t squared plus tangent of t dt, and we want to take the derivative with respect to x. How do we do this? We recognize the derivative and integral cancel. We plug in the upper limit for every t, not the dt, of course. And then we chain out, we multiply by the derivative of the upper limit. Like that. And that's our answer. Let's do another one. How about the integral from -4 to, say, sine of x of the natural log of t squared plus t dt, and we want to take the derivative. We know what to do. The derivative and integral cancel. We plug in sine of x for every t, except for the dt. And then we chain out as we multiply by the derivative of that upper limit. And that's our answer. I'll put extra parentheses here to let you know that the cosine is not part of the argument here. It's separate from it. One more problem. We'll call this a bonus problem. What if we want to do the integral from x to cosine of x of, say, e to the t squared dt, and then we want to take its derivative. What do you think we should do? The answer lies in the theory that we did above, but I'm going to put the answer, and you tell me if this is what you thought you should do. Will the derivative and integral cancel? I'm going to plug in cosine of x for every t. I'm going to chain out that upper limit. And I'm done, right? Of course not. By FTC Part I, we know we should probably subtract, well, what? Well, let's do the same thing, but subtracting on the lower limit, which says for every t, we're going to replace it with that limit and multiply by the derivative of that limit. And that is the answer.